Hey guys, you might remember looking at this particular circuit diagram a few moments ago if you're watching the videos in the order I told you to. I simply represent it here because I'm going to keep kind of zooming in on different parts of the circuit, and we'll need the progressively simplified diagram in order to be able to analyze the circuit completely, meaning answer the rest of the question. The rest of the question wanted to know, all right, fine, you've simplified this thing down, but listen, it had a 9-volt battery there. What's the charge and voltage on each of the individual capacitors? And that's what we're going to try and figure out. All right, now I realize the text might say just find the charge on the 1 microfarad capacitors, but we're going to go ahead and find it on all of them. Now, we're going to start at the end here. That's actually how you are supposed to start these problems off, is you go to the completely simplified diagram and usually begin with finding the charge on your equivalent capacitor. So we determined that the equivalent capacitance was 29/12 microfarads, or whatever that is as a decimal. And so the result we get is that with a 9-volt battery, we're going to have a total charge on the system of 21.75 microcoulombs. Great, so what do we do with that? Well, what we do is we go back up one layer of simplification. The previous layer in simplification, I had 3 parallel capacitors. They were a 3/4 on the top, a 2/3, and then a 1. And then that was what simplified down to 29/12. Well, all right, we're going to go up a layer from there, and then we have to reference the rules that you were supposed to have learned. Right? This one here is the one that we start with because we're talking about these 3 capacitors, which are all in parallel, being equivalent to this one right here. All right, so now if we look at our rules, what is the same for parallel capacitors? That's what you always have to look at, is what's the same. Talking about what splits isn't necessarily going to help you that much. Because all we can really say about that is, well, the total charge is 21.75, so that means that that's somehow divided up amongst these 3 right here. But they're all going to have the same voltage. Now, in the discussion post that you guys commented on, there was some confusion about, how is that possible? But if it's a 9-volt battery, shouldn't they all get like 3 volts or something? I mean, how can they all get 9? Doesn't seem to make sense. Well, it doesn't seem to make sense just because of how we might think about like the energy delivered or something like that. But here's an analogy that might help. Back when we started talking about potential, I said to think about it as being sort of like height. So here you see I drew a diagram of something where the height of the system is labeled as 9 volts. All right. And there's like a little elevator here lifting people up, and there they go. That's the battery. The battery lifts the little people, those would be your charges moving around, up a height, so to speak, of 9 volts. Now, what's the deal with the 3 different stairs, and why are the stairs so tall? I have no idea why the stairs are so tall. This looks extremely dangerous. But the reason there's 3 paths is because we have 3 capacitors in parallel, right? That's what I'm trying to say. We got like a C1 and a C2 and a C3. I don't really care about which one is steep or shallow. It's not important. What matters is you've got 3 different paths there. Remember, the voltage is the height. Any way you get down from this high height that the battery hath lifted you up to, it's going to be the same amount of distance down you got to go, right? So it's 9 volts down no matter which path you follow, no matter which capacitor you follow. All right, now there may be different numbers of people that go along each of these staircases, depending on whether or not they value life and limb. That's like the charge. Remember, we said this 21.75 microcoulombs will be split between those 3 capacitors. All right, so that's the split the charge thing. But since they're all the same height, they all get the same voltage, all right? So it's not a violation of like conservation of energy or something to say that all 3 capacitors get the same voltage. It just makes good sense in this analogy that the height of the system is the voltage, and all of those capacitors are therefore going to get the same number of volts because they just represent 3 parallel paths of getting from all the way at the top to all the way down to the bottom. All right, and then the people go back onto the elevator and repeat the fun all over again. All right, so returning to reality, our rule then that we're going to use first is that all three of those get the same number of volts, meaning they're all going to get 9 volts. Now, before we go any further, somewhere on your paper, you should make this table, which we are going to be filling up with values. In the first picture that I drew, I labeled all of those capacitors A, B, C, D, E, F. There were 6 of them. I now regret not... Okay, go back to the beginning of the video and look at it again. I get... Never mind. Here it is again. Just pause the video and write it down so you know which one's A, B, C, D, E, F. Great. All right, so again, they're all three going to get 9 volts. 9 volts. So what does that help us fill in our table? Well, for starters, the 3/4 farad one up at the top, we can calculate the charge on it using our C equals Q over V equation over to the left. All right, and so there it is. If I rearrange that to solve for Q, you can see that it's going to be C times V. So that means that capacitor has 6.75 microcoulombs of charge on it. And the 2/3 microfarad is going to have 6 microcoulombs, because 2/3 times 9 volts, since they all get 9 volts, is going to be 6. And the 1 microfarad capacitor gets, easy math, 9 microcoulombs. Great. Now going back to our rule for parallel capacitors, again, we use the idea that they all have the same volts to figure out the charge on all of them. But notice, if I add up those 3 charges, they add up to 21.75, which is what I said the total charge on the system had to be in the first place. All right, so brilliant. It works out the way that we said it would. Now, the goal was to figure out the charge and the volts on each of the individual capacitors. So at this juncture, actually, focusing in on the table we've got here, the only one capacitor that I actually know any values for really is the F, the 1 microfarad capacitor. That's the only one out of the 3 that I just figured out that is a real capacitor as opposed to an equivalent capacitor. But I can go ahead and fill in the values for it. All right, next we're going to go on and tackle this 2/3 right here. So the 2/3 microfarad capacitor, in the sort of previous slide, I figured out was, well, it had 9 volts on it, all right, and 6 microcoulombs. Well, that was the equivalent capacitor for the, if you went sort of back up a level, a 1 and a 2 farad capacitor in series with each other. Ooh. All right, well, so now we're going to have to go back and reference our rules on series capacitors, meaning what is the same and what is split for series. Thank goodness I know the answer. Series capacitors have the same charge, but they split the volts. Same charge, split volts. So that means that if the 2/3 microfarad capacitor has 6 microcoulombs on it, then the 2 capacitors of which it is composed has the same charge as that one. Again, when I say same, I mean same. I don't mean split, okay? So don't be like, so 3 and 3. No, I mean if the 2/3 gets 6 microcoulombs, then the 1 and the 2 microfarad capacitors of which it is made also get 6 microcoulombs on them. Now, this was again a point of a little bit of confusion, so I'm going to redraw my diagram slightly differently here to represent this scenario with 2 series capacitors. So in this one you can see, same scenario, the 9-volt battery is like the elevator that lifts everybody up to 9 volts above the ground. And then, well, and then you have 2 series capacitors, right? Capacitor 1, capacitor 2. If you like, you could argue even that these 2 series capacitors are equivalent to, one other equivalent capacitor. It lost the thing for a moment there. One other equivalent capacitor like this, all right? And either way you want to talk about it, if you look at how many people, how much charge goes through capacitor 1 and then through capacitor 2, it's the same number of people as would go through the equivalent capacitor. There's only one path. So everyone who goes through capacitor 1 must also go through capacitor 2. And that's going to be the same number of people as going through the equivalent capacitor, which is equivalent to those two capacitors combined. But even though the same amount of charge goes on each of those, that does not mean that the volts are the same. The equivalent capacitor uses up, all 9 volts, because, there we go, all the way down. All right. But each individual capacitor has a particular delta V with it, particular change in height. Okay? And so that's the splitting the volts idea, right? They get the same charge because there's only one path, but they split the volts, right? It was 9 volts up, it's 9 volts back down, but how many volts happen at each capacitor is different. All right, so back to our picture here. If then there's 6 microcoulombs on each one, and you rearrange your C equals Q over V equation, volts is charge divided by capacitance. Don't screw up the algebra there. Very frequently people will goof on that one, so I would confirm that to yourself real quick. But if that's what it is, then this one will use 6 volts, right? The one, okay, and then 3 volts. All right, and so we can then fill in those values into our table. Cool, like so. There it is. Now notice one other vital point, right? We said it's 9 volts across the 1 microfarad capacitor. Or sorry, I'm up here. Across the 2/3 microfarad capacitor. Well, either way. And also, we said the 1 and the 2 of which it is composed use respectively 6 volts and 3 volts. I do believe those add up to 9 volts, just like they should. If they didn't add up to 9 volts, then we would know that we screwed up somewhere. Well, now we got to move on to the 3/4 microfarad capacitor up there, right? This last branch up at the top that we haven't yet dealt with. Which, if you recall, was composed of the 1 microfarad capacitor and a 3 microfarad capacitor. I'm talking about, another layer back in our simplification. Okay, and then in our previous work, we had shown that the 3/4 microfarad capacitor gets 6.75 microcoulombs of charge on it, and of course carries 9 volts since it's in parallel with the other things that are in parallel with the 9-volt battery. All right, now I'm going to go pretty quick through the rest of this because it's the same process as what we did earlier in the video. All right, so now would be a good time to pause and see if you can fill in the values that ought to go here, and then see what you can fill in the table of values for your various capacitors, charges, and voltages. So pause, fill it in. All right, and zooming ahead a little bit, if the 1 and the 3 are the capacitors equivalent to the 3/4 microfarad capacitor, and they are in series with each other, then they have the same charge as their equivalent capacitor and the same charge as each other. And then a little bit of math will show you those voltage values. All right, but then this is what we can fill in our table. We do not yet know the charge or voltage on the 1 and the 2 microfarad capacitors, which made up this 3 microfarad capacitor. All right, so that takes us up a level to here. So again, pause, see if you can follow the thinking process there. It is a different rule from what you used moments ago. All right, and here I am resuming. Because the 1 and the 2 microfarad capacitors are in parallel with each other, they have the same they have the same voltage as their equivalent capacitor, because that's the rule for parallel, is same volts. So therefore, I can fill in 2 more values in my table. 2.25 volts on both of those 2 capacitors, that's A and B. And a little bit of quick multiplication later, we've got the charges on those 2 capacitors as well. All right, so at this point, you should have a completely filled in table of charges and voltages for all of your capacitors. All right, that about wraps things up. By now, you should know how to determine the charge and voltage on any capacitor in a network of capacitors. If you have any questions, please comment in the discussion in the classroom page, and I will try to address it in another video. Thanks.